Did you have registration issues?
Able to get an appointment with the counselor yet?
Oh, okay.
I have one today, so I was wondering if I could sit in
Yeah,
the
yeah,
lecture.
yeah, please do.
Okay, great, thank you.
Yeah, because I was worried about some people. I know a few people emailed me that they were like on a wait list, but I can't see a
Right.
wait list. So.
Yeah, I
There's-
called them all last week and like the week before, and
Yeah.
because I had to go up to Seattle to see family, and I couldn't, the days I was here, I couldn't get in. And
Yeah.
So,
Well, yeah, space shouldn't be an issue, so I don't know what the deal is. But
Right.
yeah, sit in,
Okay.
and hopefully they'll get you registered today, and I can send you codes if you need.
Great, thank you.
Welcome back.
How's it going?
Good, how are you?
You all right? How's your spring break?
What spring
Easter.
break?
At least Easter.
It was good.
Good?
Yeah, put on some Easter egg hunts for the kids.
Nice, nice. Do you have any people over, or did you go like?
Nah.
Yeah.
Yeah. How about you?
Pretty busy for me. I'm part of a church choir. We have kind of like the trivia before, so I basically had to be there Thursday, Friday, Saturday, and then by the time it hits Sunday, it's like, okay, I've already done like all this other stuff. I just need to relax. So it was fun. It was alright, but definitely tired.
You ready for Saturday?
Saturday. The
Magic.
volunteer
Yeah. You're still down for that?
Yes, I'm still down for that. Just let me know.
Yeah, I'll email you confirming the time. Yeah.
Okay. Yeah, just an overall kind of what I'm going to be doing as far as like, what you're needing me to do exactly for it. Is it kind of like, because I know it's like a magic show, right? So,
yeah, it's mainly like standing there and helping clean up and like Sabrina did it, so you can ask her about it, but at the end she like hand out marshmallows like frozen in liquid nitrogen while I got the ice cream going, so that's sort of thing.
okay, sounds good.
Yeah, and then like making sure, because we did the flame test, but I bring like a little portable propane torch, so making sure that doesn't fall over and stuff like that.
Yeah, no, that's
So yeah, you don't have to do too much, but
just kind of just help out here and there.
yeah.
Okay, sounds good. Sounds good.
Sweet.
Yeah.
Yeah, no.
I got $5.
Right.
How's it going?
That was good. Yeah, I totally agree.
I think they should have done like 3 weeks and 2 weeks, not more than one.
Yeah. I know. That's all above our pay grade, so.
Teaching chemistry is
Oh, did they use the sandwiches on my car? And when we got Right, I could go tacos.
Is this your first term? I noticed, but I wasn't sure if it was intentional or not, so I just. Like, that was literally, well, also like, the one like last term, well, now I gotta like try. I didn't get very far. I was having a hard time.
All right, let's go ahead and get started. I feel kind of weird calling roll, but I guess I don't know. I'll just kind of go through it. And then is there anybody not registered that needs to register? So everybody should have made it over from Chem 222 to here. So everybody passed, so I don't know. Like, I don't know where Tyler is. He's not on my roster. I don't know if he just didn't need this class. Yeah. I encourage people to take the whole year just so you don't have transfer issues. So if you see people around that aren't in this class, you might want to tell them that they might want to complete it. Yeah, because it creates transfer issues. All right. I guess I won't really call roll. So Phoenix, Andrew, Rebecca, I assume is online. Cabrina is here. Cora, I saw. Audrey, Meshach, Savannah, Riley, Jonathan, Eugene's not here, but I assume will be on. Let's see, Trenton, Madden, Matthew, Keller, Carmen's not here, but I assume she will be. Bree, Alira, Tori, Josue, Matthew. Oh, there's Rebecca. We were just talking about you. Camilla, our new student. So welcome, Ariana. She has to deal with the rest of you guys. So they all know each other. So yeah, help her out in joining our class. So and there was Carmen too. We were just talking all about her, and Christy. And so, gents, you're the only one that hasn't registered, but you said you're going to register. And then nobody else had issues registering. I think I have one person by email, but he's not here today. All right, let's just talk about the syllabus really quickly. So your syllabus is still in progress, let's just say. So I've been working on your Oregon Caves field trip since last quarter, and the email is really slow back and forth. So they have not gotten back to me with a date. So at some point there's going to be an Oregon Caves field trip, and so this Lab 8 might go away. But let's just take a quick look. So it'll be the same format how I've been doing it. So you have your homework, lab will be given out to you. And then of course you're either in my Tuesday or Thursday lab. And so we have our first lab, and I'm trying to just cram all the labs in because, and I don't have this on the syllabus, but I'm going to give y'all a heads up. So I've been slated for jury duty this week. Yeah. So talk about my stress levels this quarter. So, and so what I'm hoping will happen is it's exam week. So if we have to kill that week and not have lab, that's kind of what I'm planning for. I'm hoping the Oregon Caves won't happen that week. But yeah, that's kind of what we're avoiding. And then hopefully we'll have our field trip this week, and then that'll kind of shift the labs down then. So then Lab 5 will move, Lab 6 will move, Lab 7 will move. So this Lab 8 will probably go away. And then we're not going to have a lab practicum this quarter. So we're changing it up a little bit. And so, right, we have our paper that we've been working on, and so I still need to work and edit your paper, so spring break was not long enough. But what we're going to do is turn those papers into a little mini poster presentation. And so we kind of want to practice the style that would be done at like a conference. And so this is done at like ACS or like any conference where there's a poster presentation. You just have a room full of posters, and then people kind of walk around casually. And so I wanted to do the same thing with this class. So we'll have, some snacks, some refreshments, and then probably trade off. So my idea, since there's only, 24 or 25, 26 of y'all, is it would be nice if we could meet on the same day that last week. I don't know if that works for people's schedules. But ideally, we could combine into one lab section, do half the class, give their poster presentation to the other class while, you walk around, chat, again, real casual, and then switch at the halfway point or something like that, and then have the other class present. And again, it's supposed to be like low stress presentations and more fun than, getting up to in front of the class and giving a talk, so that's more stressful. So trying to practice that low stakes poster presentation. So that is basically the year. So again, same formats. So be having quizzes like we've been having.
Will there be a quiz this Thursday over chapter 20?
No, so the quizzes will start next week on chapter 21. So I will do a welcome quiz for y'all. So you'll still have that. So that'll happen on Thursday. I think that's, I did want to say, so do you all have class before this? So what time is your class? Because I'm trying to plan the Oregon Caves trip. Because it's like almost a 2.5-hour drive time. So I'm trying to figure out when we should meet. So then you could. How late does yours go? So is everybody end at 10?
Mine goes till 10:50 on Thursday.
That's the other option, but I hate making y'all like have to miss your morning class. Because
Our
if,
field trip is more fun.
I mean, I would like to argue that. Yeah.
More hands-on.
I hadn't planned it for a Friday because I think some people have work stuff. I could try to get back to them because I'm also trying to work on coordinating. So what's awkward is like in Grants Pass, the same class, the CHEM 223, they do theirs on Monday and Wednesdays. So I'm trying to work and see if we could do one field trip on Wednesday, one day on Thursday. And then I don't know if that works better for anybody to go on like the Wednesday with their class, but Monday, I don't have a Monday option, but yeah. And so that's the other thing is, so there will be an alternate assignment where you can either go to the Oregon Caves on your own, or if you can't make it out there, you know, you can like do something alternate. So there will be alternatives, but it would be nice to try to get the whole class there. So I'm trying to figure out what time. So what, it sounds like for most people, so 10, so like what, 12:30 at the earliest, maybe optimistically, or 1.
You mean getting there?
Yeah, like starting, because I'm trying to coordinate with them still a start time. I'm not, because I think they say it's 3 hours total, but I don't think the cave tour is 3 hours.
The cave part is not for
Yeah, I think it's for
too
like
cold in there.
1, maybe 1.5. Yeah, it's pretty fun. All right, any questions about the class or anything, what we're looking towards this quarter? All right, so let's just dive into it. And so you'll notice, so I have the live link going, so it's under the lecture notes. You'll find the live link. And so basically we're continuing where we left off, right? So think back to just a week ago. And right, we were doing rice tables, equilibrium, weak acids, weak bases. So we're basically continuing that. And we'll just kind of see it's more, I would say, applied or more complicated, what we're going to be looking at. But you should have all your fundamental knowledge from last quarter of how to do this quarter. And so we start off with our introduction. And so antifreeze is pretty toxic to your pet. So, of course, antifreeze contains ethylene glycol, so you may not also be aware of, but there's ethylene glycol in like those little snow globes. So if your snow globes ever break, I assume they're put away now since it's not Christmas season, but if those break, you want to clean it up right away and make sure your pets don't go to it because they're going to want to drink that since this ethylene glycol has a sweet taste. And so very dangerous to pets though. So it's this initial effect of drunkenness, but then it's metabolized in the liver to glycolic acid, which is toxic. And so this explains why. So in high enough concentrations, then this of course affects the blood's ability to buffer. So it overwhelms our bicarbonate and causes our blood pH to drop. And so then we have our equilibrium shown here. So of course it binds then to our proton instead of binding to the oxygen that our hemoglobin, right, is supposed to be transporting around the body. And so treatment for this would be to give the patient ethyl alcohol since that has a higher affinity for the enzyme. And so we're going to be continuing to look at this. So right, we talked about buffer solutions last quarter. And so now this is a refresher. So we said that buffer solutions were just solutions that resisted changes in pH when you had an acid or a base. And so we mentioned how to make it. And so this was kind of, right, the key starting point. So we said we had either the weak acid and its conjugate base, or the weak base and its conjugate acid. So what system do we remember? Kind of, what was a classic example? Or even just any example? Yeah. Acetic acid and acetate, good. So that puts us in the mood there. So acetate, so we can think about, oh yeah, that's what was going on, and we can draw out, right, our acetic acid, kind of remind us. So there's acetic acid, right, becomes acetate, so deprotonated. Okay, so now we're kind of remembering, and I'll put a little sodium there so we can remember, right, it's sodium acetate or potassium acetate, so some salt. And okay, here's another buffer mixture to kind of remind us what's going on. So we have our carbonic acid and then our hydrogen carbonate ion. And again, just a difference of a proton. So there's our acid base pair. And so here's the example y'all stated. So I think this was a scene from, again, last quarter, just reminding us how we made our buffer, so combining our acid and our base. And so we had, again, looked at this last quarter, so this is kind of a reminder, because this is what we're going to be doing kind of next as we go on, kind of mathematically. And maybe you even peeked at your homework. And so now this is kind of what we're going to be doing, again, words. And so if we are looking at our acetic acid buffer solution, so acetic acid acetate, and let's say we add a base, so then we'll do the math, right? So essentially we have to do our stoichiometry first, figure out our neutralization, right? How many moles were neutralized, how much of our conjugate base was formed, and so we'll again be doing that. So this is just putting us in the right frame of mind. And again, same thing. So what happens if we add our acid? Again, we're still thinking about our acetic acid sodium acetate buffer situation. And so in that case, our acid will be neutralized by our base component. And so again, we can look forward to doing the math, right? So we'll have to figure out how many moles were neutralized, how much of our acid was reformed from that neutralization, and then of course calculate our pH change. And so again, this is mainly a refresher. So just reminding us, so again we add our base, and we reform our conjugate base here. Same thing, adding acid. Then we make our reformer acid. And so we're kind of skipping that. And so we're basically getting at our common ion effect. So now this is, again, going into our Rice table. And so again, just given any equilibrium situation, so we have acid, and then of course, right, makes our conjugate base here. And so now all we're saying is, so we could add a salt then. So we could, let's just think back, so we're still thinking of acetic acid sodium acetate. And now it says, well, what happens if we add more sodium acetate or lithium acetate, right? Maybe it's not the same. But what happens if you add more acetate to it? And of course, right, we would expect it to shift the equilibrium. So thinking back to Le Chatelier's principles, so of course, we're making more conjugate base. So then that's going to shift it and make more acid. And so then, of course, right, our pH should change. And so let's just get into it then with our math here. And so calculate the pH of a buffer solution that is 0.1 molarity in our acetic acid and sodium acetate. And so how might we set that up? Again, thinking back to what we were doing last quarter. And you might also remember a formula from last quarter too that we could bring out. Oh, and I probably should have given you the pKa, so that would be helpful. So the pKa is 4.74 for acetic acid, and so now let's at least kind of touch base and figure out where we should be. So write out your equation first of what's going on with our equilibrium. So we have our acetic acid, and we're trying to calculate pH, right? So that means, well, we're with water. We need to figure out how much hydronium we have. And of course, right, we started off with some acetate. And so the first thing we should do is just write out our initial conditions. And so this is hopefully how far we made it, at least from last quarter. So it says, okay, we have 0.1 molar solution of our acetic acid, and then 0.1 molar solution of acetate. And so this is, right, initial conditions. So nothing has happened, nothing's disassociated. And so this is kind of maybe the next tricky part, is that we have to realize, right, well, we haven't formed any hydronium yet from, right, our scenario. So we just have our initial conditions. So then for our change, this means that this is minus X, and some of it has to disassociate to make at least some amount of hydronium. So we don't know how much. And then, of course, that means that if we make hydronium, we make more acetate as well, so plus X. And so now this is hopefully looking familiar. So now we have our equilibrium, just like before. So plus X, 0.1 plus X. And so now we can set our expression and solve. And so this is just our reminder. So of course, right, our Ka acid expression is just hydronium times our conjugate base over our HA, so our acid. And then I need to solve for my Ka. So, right, Ka is just equal to 10 to the power of negative 4.74. So again, just a reminder. So then we should get a Ka of 1.82 times 10 to the negative fifth. And you could have had slightly different numbers potentially if you looked it up, or so some discrepancy. And then from here, it's just solving. So I'll plug it in, 1.82 times 10 to the negative fifth. So plugging all these values in. So x is hydronium, plus 1 plus x, conjugate base, and of course plus 1 minus x. So I'll pause there. So did we all make it there? Does that sound familiar? Clearing the cobwebs. And so now it's just math at this point. So I'm going to go ahead and try to make our assumptions. So remember that. So let's make our assumption that x is less than 5%. And of course, right, I've said you're welcome to also plug this into Wolfram Alpha. So I just want to see this shown out, since I know all the math gets tedious. But I'll see if my assumption works. So 1.82 times 10 to the negative fifth equals x times 0.1 over 0.1. And so then we get x is just equal to our Ka, which we want to check. So take this over our 0.1 molarity, right, since that was our initial conditions. And that should be less than 5%, just judging from this 10 to the negative fifth. And so yes, right, that was super tiny, so 0.018%. So assumption was good. And so now we can plug in for our pH. So now pH is negative log of hydronium, which was x. So 1.82 times 10 to the negative fifth. Yeah, which gives us back, which now I feel silly punching this in, but we'll punch it in. And so yes, gives us back our pKa. Does anyone remember the formula from last quarter? We didn't really use it too much, but it may be more helpful now. Anybody remember what it was called? Or I'll write it. Yeah. So if you remember, so now we can recall. So let's compare our answer. So compare to our Henderson-Hasselbalch equation. Oops, if I could spell. And so if you remember, there are two forms of this equation. And so I like this one. So pH equals pKa plus the log of base over acid. And so it's a plus sign. If you do base over acid, you might see pKa minus log of acid over base, so same thing. And so let's just compare. And so this actually will show us how we got the same answer. And so, right, let's just read back the problem. Well, we started with equal amounts of acid and conjugate base. And so if we were to plug that in, so then we have the pH is equal to pKa plus log of base over acid, which is 0.1 over 0.1. And so what's the log of 1? So 0. So that cancels out. And so now we're saying, right, when our base and our acid are equivalent, then your pH is equal to our pKa there. So that canceled. pH equals pKa, which is what we got. So now we're back at the beginning. And so now we're just reintroducing Henderson-Hasselbalch. So here's our equation again, in case you didn't write it down. And so this is useful when we can make that assumption. So again, it is only valid when x is small, approximation is valid, and then we can skip and use Henderson-Hasselbalch. Otherwise, then we have to do our good old Rice tables. And so you can note that, right? So Rice is always good. So, right, our Rice method always works. So, right, if you're ever unsure on a test, definitely use Rice. Uh-oh. Come back. There we go.
So this kind of has the assumption built into it.
Right, yeah. Yeah, so if you're doing it, then you are making that assumption.
I think there's multiple requirements where like your textbook where it's like, oh, you need all these requirements to use this equation. Or like it's like 1, 2, 3 like rules for it.
Yeah.
Yeah. It's like, oh, the molarity needs to be in a certain range too.
Oh, yeah, it's probably said something that like it can't deviate. Yeah. So let's continue. And so let's see, blah, blah, blah. So we kind of saw this. Sorry, equilibrium arrows got lost. So this is just the derivation for it. Oh, yeah, and so this is what Andrew was mentioning, that when can we use it? So your textbook mentioned certain conditions. And so again, right, not always applicable, but for the most part, we can use it, again, when we see it in this class. So we said X is small approximation. And so it also mentions, right, initial concentrations of the acid and salt are not very dilute. And, you know, so just talking in the range that we've been doing, 0.1 molar, 0.01 molar, 1 molar, right, that's all fine. But if we do something really tiny, then this assumption may not work. And then the Ka, again, has to be fairly small. So that's where that X is small approximation kind of comes into play. So we saw that, right, 10 to the negative fifth. But if you get kind of too large, so like 10 to the negative third, that's where I'd be more wary. And it also mentions, right, that your initial acid and salt concentrations should be over 100 to 1,000 times larger than your Ka. And again, your Ka is usually pretty small, so that is usually the case. So. All right, so let's continue practicing. So hopefully that makes you feel better about this chapter, is that it's essentially what we've been doing, just applied. So let's try that again with our benzoic acid. And I would go ahead and try both methods. So let's try it with the Rice method first, see what that gives us, and then compare it with Henderson-Hasselbalch. And so I'll let you start that. So I filled out the rice table. So did everybody get our equilibrium? So again, you're just identifying, right, who's our acid. So of course, benzoic acid and 0.05 molar solution, 0.15 molar solution of our conjugate base. And I just kind of abbreviated, right, HA, H plus, and A minus to remind us. And then because we had no hydronium, that's why we did, right, the minus X plus X plus X, just like previously. And so then I assume you made it to here. And then from here, right, we could do the math. And I assume most people made the assumption from our 6.5 times 10 to the negative fifth, so that's kind of small. And so I'll set up our equilibrium expression. So if you got to here, again, good point. And then make our 5% assumption. So then we can get rid of this X plus X minus X. So then that simplifies. Oh, there's a bug crawling on my computer. So we get X times 0.15 over 0.0. It's one of those like box elder bugs or something. And so now we just solve. So I get this for X, so 2.166. I see some thumbs up. So X equals 2.16 times 10 to the negative fifth. And then you want to check our assumption again. So divided by 0.05. And so just like we expected, right, super tiny, so 0.04%, so that was good. And then this is our X, which is hydronium, so now we can plug in for pH. And so I get like 4.67, depending how we round, so 4.67. And then did we get a chance to plug it into Henderson-Hasselbalch?
I did, and I got 4.66.
So got 4.66, so pH equals pKa plus log of base over acid. And let's see, so we were given the Ka, so we have to find pKa. So negative log of our Ka. So now we have 4.19. And then again, just identify, right, who's our acid. So benzoic acid, so 0.5, or excuse me, so 4.19 plus log of base, so 0.15 over 0.05. And so I got the same thing as well, so 4.66, 4.67. So depending how you rounded, try the pKa as well. And so,
Why do a lot of the equations in the textbook, they'll have it where, like finding pKa, you'll have the log or the negative log of that Ka, but then divided by the polarity. But a lot of the time
So it depends, and also whether we change the volume. So here we didn't change the volume at all, so I didn't really worry about moles and molarity. There are other situations, like especially when we're doing our lab titration, right, where your volume is going to be continually growing. So then you have to recalculate the molarity every time. So yeah, it kind of depends. So in this case, yeah, I was a little sloppy. Yeah, but we weren't changing the volume, so we didn't have to worry about going from moles to molarity. But that was a good catch, because that will be a problem. Yeah. Yeah, it all depends on volume change. All right, so let's try another one. So this is similar to the approach that we've been doing. So go ahead and try that again, so you can't have enough math practice.
On a test, would you want us to do like both methods? So that we can do both methods?
Yeah, it would depend on the test, because like I would either say like solve, and then you could use whatever method is appropriate.
Right.
Or yeah, I might say use a rice or use both and compare.
Can you zoom in?
Oh, sorry. Yeah, it's good practice at least to do both. Get really speedy with your rice tables. So let's check in with everybody. So we can do our rice method. So again, pretty repetitive from like the other ones. So again, we started off with acid and conjugate base, no hydronium, so minus x plus x to give us this expression. And then I assume most people did the 5% assumption at this point, especially with our 10 to the negative 10, so that was pretty small. And then what do we get for x?
I got 7.21.
So that sounds good, and I see some other nods. And so we plug that in, so log. So then we get, oh, I didn't put my negative sign, so about 9.14 for our pH. So I see a lot of thumbs up. And did y'all plug it into Henderson-Hasselbalch? So I hear people got the same thing, so pKa plus log base over acid. And they gave us a pKa, so we didn't have to solve that. So 9.31 plus my log. And so which one was our base? What number? So 0.17 over 0.25. And let's just plug it in for good measure. And so that matches, so that looks good. Any questions on kind of what we've talked about so far? So this is probably a good point to take our 10-minute break. So we'll take our 10-minute break, and then we'll go back to similar but different problems. So I'll put this up here so we can look at where we're going. But take your 10-minute break, and if you have questions about what we've just done, I would get help during the break before we keep just moving on. Yeah, or you could just do it like next week or something.
Okay. Yeah, it's not a big deal.
Yeah.
Okay.
How's it going?
Okay. I was wondering, so for the assumption, basically that's just letting you be able to like get rid of the plus x and the minus x.
Yeah, because you're assuming that your change in x is so small compared to these initial conditions that it's less than 5%.
Oh, okay.
And so that's why it goes away with the addition, subtraction stuff.
Okay, that makes more sense. Thank you. Oh, and then I also have a question. So like the lab is part of the lecture grade, like it's all lumped into one. Okay. I'm gonna have to figure out with work like how to get some time off for it because I work right after this.
Oh, no,
On
yeah.
Tuesdays and Thursdays, so but I'll try to see if I can get one of the days off.
Yeah.
Or switched. Okay, thank you.
Well, I'll hold you to that. Remember my cool name.
Like the beginning, like the very beginning.
Or well, I didn't even remember bringing because it was working as before.
Little tables.
Or like periodic tables. Oh, I can make some more. I think people will grab them. Yeah, I think
I could just print one off at home.
Oh, no, I have time because I'll do it on the card stuff.
See, I've always had like,
Yeah, it's like, oh, I didn't it's really all the yeah.
Was he like, was it? He was like doing weird things with himself. And she was like, is that okay? And I was like, no, it's not. And I never talked to her again. I don't know. They were just like regular. They were just like,
you walked up, you started saying,
yeah, I guess I'm your Jim.
every time I see her, I do it. Every time.
first day back. Neither of my grandmothers, both sides of the family, really approved of them. Yeah, and I didn't want to explain to them like vaguely told them the information they needed to know just to make them back up. They continue like to feather some information in there, until they like let it go. Yeah. I told them. Told them. Great fun time.
Because I was quite so much of the work. Because I just kind of chill out in classes a bit if I'm already
So, white wine.
yeah, I'm just gonna take whatever.
Yeah, right.
Might as well get good.
Yeah.
When she tells you like exactly what you want, exactly
Weird
what
that they would very judgmental.
and then you just read that.
Because my my grandma's son and my
So you're supposed
she
to,
married,
it's supposed to
they
open
both have tattoos.
applications in April, they're supposed to submit. So I kind of see like when the
They're
month
just
starts,
like,
but they haven't updated their
they're
website
just
yet.
like, you know, they're leftovers.
So we can check. I know we're working hard.
It's like you look in a bunch of seasons.
No, I just have like,
They're just like,
I didn't even know you could make it until Ishak told me about the bookmark folder thing. I didn't even know that they were a thing. I was like, dude, wait, you're the bookmark is like, oh yeah. In their absolute chaos of like doing that. I was like, but yeah,
crazy for a moment. I thought I was feeling better.
Folder is
folder. So it made me feel good. So. Oh my. My dad, I realized my dad's a that's why he made it through. We're not to talk. He was a
So far, as far as classes are concerned, I'm not really worried about that. As long as I just continue to graduate. Sorry, I know how it is for like, no, I know how it is for like, say, high school transfers who like, basically right out of high school. It's a lot more expensive. It's kind of a way, I feel like it's themselves, which is, no, it is very good, which is frustrating. Thankfully, because I have basically been
I'm not kidding, I'm not kidding.
transferred over to a higher first semester. Didn't have to worry about that, except for,
You didn't push in your chair either. I pushed it in for you, actually.
Well, that is fair.
Yours was like all the way out.
I think I was like, I moved back a little bit.
Yeah, you kind of like.
Ohio sucks.
All right, so as you come back, so you can try this one out. And so notice the first part has us do Henderson Hasselbalch again. And so don't forget, right, who's your acid, who's your base in this one. And we have a PKB, so it could be some trickiness. So start with that, and then we'll start looking at the second half. So did we figure out how to get the pKa? Do you remember that? So we have to think back to, we have two different relationships to work with. So we have Ka times Kb was equal to that Kw, which was 1 times 10 to the negative 14. But then we could derive that, and then we get pKa plus pKb is equal to 14. So this is also a useful relationship. So what do we get for the pKa then? So 9.25. So we should have gotten that. And then so Henderson-Hasselbalch, so pKa plus log of base over acid. And then which one is our base? So the ammonia, right, so NH3, or the 0.5, and then so, right, this is our acid, so ammonium, so just make sure you plug that in correctly, so 9.25 plus log, so then my base was 0.5 over 0.2, and so then we get a pH of 9.65. Is that what everybody got for that one? All right, so now let's do this part together and what it's saying. So now it's saying, okay, well now we have 1 liter of this solution with, again, our 0.5 molar of ammonia, 0.2 molarity of our ammonium chloride. And so now calculate the pH if we dump in 0.01 moles of solid sodium hydroxide. And so just to kind of, again, remind us, because it was brought up earlier, so right, our volume is not changing, but let's go ahead and convert everything to moles, right, because we have molarity versus moles. And so let's set up our rice chart just like before. And so I'll just rewrite it. So we want to add 0.01 moles of NaOH to our buffer. And so now we want to just write out kind of our reaction, right? So what's happening? So we have sodium hydroxide. And so now let's think about, so which one is it going to react with? So the ammonia or the ammonium chloride? So the ammonium chloride, so that's our reaction. And still equilibrium, right? So then it forms our salt. And then, of course, makes our base, our ammonia. And so now we can put kind of our initial conditions. And so let's convert everything to moles as well. And so I'm going to start off with 0.01 moles of sodium hydroxide, even though, right, it's probably all going to get canceled out, but we should keep track of this. So again, this will apply to your homework, right, because first you have to see, well, is all my base neutralized by my acid, or is my buffer, right, completely overwhelmed, and now all I have is sodium hydroxide. So that's kind of what we're doing. And so we have 1 liter of solution, so right, just multiply, so that means we have 2 moles of ammonium chloride, right, in 1 liter, 0.2 moles. So 0.2 moles initially. So we haven't done any math, right? And then we have 0.5 moles of ammonia. So this is just saying we added it. We haven't reacted it, is kind of the way to think about it. And so now you can kind of do this change, or change plus equilibrium, kind of what makes sense to you, because now we have to do the stoichiometry, so that's the first step. And so this is going to go away, so now we can subtract, right, our neutralization reactions. Now we're left with 0.19 moles of ammonium chloride. And so now if we're neutralizing, then we also make 0.01 moles of ammonia, so plus our initial moles. And so now, right, we consumed it all, so we could put 0, 0 there just to, again, kind of remind us. And so at this point, we would be okay to do Henderson-Hasselbalch. So we have our new amounts right after we did our neutralization. And so, of course, we could do Henderson-Hasselbalch at this point. So now I'm just going to abbreviate this as HH. And so I'll rewrite, so pKa plus my log of base over acid. So from before, we'd said the pKa was 9.25. And then now we have slightly adjusted totals of base and acid, so plus the log of 0.51 over 0.19. Oops. And so we get a pretty small change in pH. And so, right, we kind of expected that it would be a higher number pH as we're adding more base. And so, yes, that happens, right, 9.6. We'll round it to 8. And it's a pretty small difference, though, right? We started with 9.65, but that makes sense, right? So we said the buffer resists a change in pH. So that makes sense that even though we added our 0.01 moles of sodium hydroxide, our pH only went up a little bit. Questions about this part, kind of how we did it? Yeah. So this is, it's just a shortcut, right, to give us the pH. Because that's all we wanted to find for that problem, right, is basically we started with a solution that was 9.65 in pH, right? And then we're asking, well, what happens if we dump our solid? And then the Henderson-Hasselbalch just gave us a quicker way to, plug in for our new base over acid and get our new pH. Oh, so that came from, so we took the 0.2 moles initially, right, of our ammonium chloride, and then it was reacted with our sodium hydroxide, so they neutralized. So then we took the 0.2 minus 0.01 to give us 0.19 moles of ammonium chloride left. And then oh, yeah, so it makes our water, but yeah, since we're just looking at our kind of neutralization, looking at our, again, base versus acid species. Yeah, because the water is also not part of the equilibrium expression, so. Other questions on this one? So there'll be much more of this to come. And so now we can kind of at least take a step back and kind of realize what these equations have been telling us. And so, of course, a good buffer should be able to neutralize moderate amounts of acid or base, but obviously, right, there's a limit to how much can be added before our pH changes significantly. And so I always use a term like we are overwhelming the buffer. So of course, right, if we had added 0.2 moles of sodium hydroxide here, we would completely have neutralized our ammonium chloride. So that would be our equivalent point. And so our buffering range then is the pH range at which the buffer can be effective. And so then we have our capacity, which is the amount of acid or base a buffer can neutralize. And of course, that depends on your relative amounts of acids and bases, and then of course the concentration. That makes sense, right? So of course, obviously, if you have more moles, then it can neutralize more moles back. So
What does it mean by relative amounts of acid and base?
so that's coming up right next.
Okay.
So what it means by that is that the buffer will be most effective when your base and acid, so again, our buffer solution, so we're thinking of, let's just say, acetic acid and sodium acetate. So that's most effective when they're equal, so equal concentrations of our weak acid and weak base, or again, ammonium chloride. And so it says, right, it's effective when it's in this range, so anywhere from 0.1 to 10 difference, and then outside of that, again, it loses its effectiveness. And of course, right, again, it's most effective when our concentrations are large, so larger molarities. So that kind of makes sense. Leave that there for a second. And again, right, obviously a more concentrated buffer can neutralize more acid or base than a dilute one. So just thinking of like a 3 molar versus a 0.3 molar or anything like that. And so again, our buffering capacity is our amount of acid or base that can be added to our buffer without causing a large change in pH. And so our buffering capacity increases, again, with our absolute concentration. And of course, we want this ratio to approach 1. And so then that enhances our ability to, of course, neutralize either acid or base that could be added. And then this would, of course, be for a more specific situation, but if you're trying to tailor your buffer that needs to handle acids, then of course, right, you might want to have more base than acid in your conjugate base salt. And so same thing, so let's say you need to mainly neutralize bases, then you might want to have more acid. And so let's kind of think about this. So which acid would we pick that could get a salt ratio at 4.25? So how would you solve that? So this is a good question, because how could we design our buffer? And so what are our initial thoughts? So which one of these is closest to 4.25? So formic acid, so I like that. So first, right, all we've done is selected, well, which one's the closest to our desired pH? And so I like formic acid. And so now it says, see if we can calculate our ratio then of conjugate base to acid. So again, how would you make this? So we're in lab, right? We want a pH of 4.25, so we've selected formic acid. And so let's set up our Henderson-Hasselbalch. And so we said, okay, well, I want a pH of 4.25. My pKa is 3.74. And so now we just need to figure out our ratio of base to acid. And so now we just need to do the math here. So 4.25 minus 3.74. So then 0.51 is equal to our log of base over acid. So let's get rid of our log. So 10 to the power of everything. So 10 to the power of 0.51 gives me that number. So 3.24 is equal to our base over acid ratio. So we need a little bit more base than acid. And so what could we say then? What's our formula? What's a sample formula? Yeah, so what would you mix together in lab then? Excellent. So like he mentioned, right, we need 3.24 molarity of our formic acid salt, so I would put sodium formate or lithium formate, something. So I usually pick sodium since it's cheap and abundant. And then, yep, formic acid, so this would be perfect, so this would be a good buffer solution then. Questions about this problem? And so now we're getting to the titration part, which we've done before, but again, you get into lab today, and then you'll kind of do some titrations with weak acids and polyprotic acids, so you'll kind of see the difference. And so the first part of these notes, I think, is just a repeat. So we, of course, mentioned we're trying to reach an equivalence point. And so usually, right, this equivalence point is where our moles are equal to. So where, right, our acid moles equals our base moles. And then, of course, right, we choose appropriate indicators. So now we're kind of thinking to these sorts of scenarios, like, okay, well, what pH am I aiming for? Again, you don't have to think about that for your lab in particular, but just kind of for the future. And of course, right, we have our endpoint that helps us see that. And so we've seen these titrations. Let's kind of look into what has changed. So we went over this kind of briefly last quarter, but now let's kind of go over it again. And so when we titrate a strong acid and a strong base, so if you remember, this has a pretty sharp equivalence point, and then we're just thinking about, again, where acid equals our base, and so that's going to be 7 for our strong acid, strong base solution. And then, of course, right, our pH changes a lot, so we go from, of course, a very low pH, and then it shoots up right past the equivalence point, and then it's a very high pH with our excess hydroxide. And so if we look at a weak acid with a strong base, so it's a little bit different, and there's some key points that we want to look at. And so prior to our addition of our base, right, we can determine our solution pH just like a weak acid pH problem. And so this is kind of what you'll have to go through in lab, and we'll keep practicing the math. And so this is, again, essentially what you did here, right? So before you reach your equivalence point, it's a buffer solution. So you're adding some amount of, base, let's just say, to our weak acid. And so we have to calculate, right, our reaction stoichiometry first, take into account how much was neutralized, and then you can use Henderson-Hasselbalch to help you, so you'll do that. And then this is kind of useful. So this is, again, for your weak acids and strong base. So your half neutralization pH is equal to your pKa. So that's your halfway point. So that's kind of a good check mathematically. And so again, just think about how your titration curve is going to be different. So your weak acid, so it's not going to have as low as of a pH as our strong acid, right? So it's a little bit higher in that 2 to 4 range, or 3 to 4. And then we have our equivalence point again. And then, of course, once we get past the equivalence point, then it's basically a strong base problem once we've overwhelmed our buffer there. And so let's practice that, or start practicing that. And so let's just start with A for a second. And so see if you can set up the reaction. So I'll give you a few minutes to kind of set it up, and then we'll kind of see what we've thought about your setup. And so remember, you want to probably convert to moles and kind of watch everything. And also, let's keep in mind total volume. So this is where that total volume is going to be relevant. So now your volume is always changing. And so let's just go through initially what y'all did. And so, of course, first identify, so we have a strong base, and then strong acid. So no equilibrium to worry about here. I'm still going to write out kind of our reaction, in a rice table just so we can see. And so I'm just writing what we're doing. So sodium hydroxide plus our nitric acid, of course, gives us water, and our salt. So then our pH is probably going to depend on our hydroxide concentration. And so how many moles do we have initially? So let's see. We have 50 mils of nitric acid. So how many moles of nitric acid do we have to begin with? Oh, sorry, you're right. So 50 mils of hydroxide. So how much do we have initially? How many moles? So 0.01 moles of sodium hydroxide. And then we react it with, so 30 times our 0.2 molarity. So how many moles of nitric? So 0.2 times 30, so 0.03. So then we have 0.006 moles, right, of nitric. And so what happens? Who gets consumed? So our nitric acid gets completely consumed, so minus 0.006. And what's our total volume, though? So we added 50 mils plus 30. So we're at 80 milliliters. And then we were left with 0.004 moles, right, of sodium hydroxide. And so now we're here, so we're good to solve for molarity. So molarity, moles over liters. So now we can calculate our new molarities. So we're left with 0.004 moles of sodium hydroxide over our 80 milliliters, so converting to liters. Oh, sorry. 4.08. There we go, that looks better. And so then we can take the negative log of this, so this is, right, our molarity of sodium hydroxide concentration. So then we can solve for our pOH. So now this is our pOH, and then 14 minus that, so about 12.7 for our pH. All right, what about B at the equivalence point? Do we need to do math for this one? So no math required, right? Strong acid, strong base. So at our equivalence point, so, right, hydroxide equals hydronium, and we will have a pH of 7 then. So again, that's for our strong base, strong acid scenario. All right, let's look at kind of the words with acids and bases, and then we'll keep doing these practice problems. So I think we saw this. It's like we said, half neutralization, blah, blah, blah. All right, I think this is just repeat, actually. All right, so let's try another problem. So now a similar scenario, but what's changed? So what changed from the previous problem to this problem? So they don't have the similarity, but then what else is the issue? So this is a, yeah, but then this is a weak acid. So now a little bit different. And let's see how far we get. And so see if you can calculate A, what it's asking for. So remember, what is the definition of your equivalence point? So just try that on your own for a second. So what do we get for A? Walk me through that. So what's the equivalence point mean? So when our moles of our acid equals our moles of our base. And so we can calculate our acid moles. So I think that's probably the best way to start. So we can take our 0.1 times our 40 milliliters. And so now this gives us 0.004 moles of acid. And so if we have this many moles of acid, right, we need that many moles of base for our equivalence point. And then, so how many milliliters is that to give us 0.004 moles of KOH with this solution? So 20 milliliters. And right, we can just divide. So divided by 0.2. So that gives us 0.02 liters or 20 milliliters of KOH. So does that make sense for the first one? So the first one is just, again, definition. So now see if you can try B. So B should look like a little bit of stoichiometry. So probably have to calculate moles and volume. So go ahead and start that. yeah, you might need the pKa. So let's see, the pKa is 3.34 for our nitrous. So I'm just going to start going over B. And so the first thing that I would suggest doing is just writing out your reaction again. So our nitrous acid is being neutralized by KOH to form water. And then, of course, our potassium nitrite. And so I'll just kind of put a reminder as to why we need our Henderson-Hasselbalch here. So of course, right, this is making A minus, so a basic salt. And so this is just kind of an aside, right? But what we're kind of thinking of is well, if we make more of our conjugate base, right, going back to kind of our Le Chatelet's principle, well, that's going to go ahead and re-react with the water, right, to give us back our nitrous acid and, of course, hydroxide. So, right, we have that equilibrium expression going on, so that's why we need our Henderson-Hasselbalch, right? So that's kind of a reminder of how our buffer system is working. And then, so from here, it's just setting up our math. And so just like before, right, well, we still have 0.004 moles of acid, right, from our initial conditions. And so I just put that under there for initial, so 0.004 moles. And then how many moles of KOH was this? So that sounds good. I'll plug it in, but just like y'all said, 001 or 1 millimoles. So, and again, right, nothing initially. So then we can do our reaction. So then it reacts, or however you want to think about it, right? So change plus equilibrium, reacting them now. So all this goes away. So all our potassium hydroxide, right? So we have less. So that's all gone. That leaves us with our 3 millimoles of our nitrous acid. And then, of course, we form, though, 1 millimole of our base, so potassium nitrite. And Don't forget our new volume, although it actually ends up canceling, so it doesn't matter too much. So we would calculate our new volume, so it should be 45, right? So 40 plus 5, so 45. But if you notice, if you take, right, 0.003 over 45 and 0.001 over 45, that kind of cancels anyways, but good to check. So then we can plug it into Henderson-Hasselbalch. And so now we have, sorry, rewriting this. And then so that gives us 3.34 plus my log of base. So we had 0.001 of our base salt divided by our conjugate acid. So is this what we got for our pH? Oh, yeah, I gave it to you, but you could also look it up. So let's look up, what does Google say? Nitrous acid pKa. They have 3.16. I had 3.34 for my notes, but I'll put, yeah, and that's where always showing your work comes into play. So if you, again, I had 3.34. I'd have to look at our old notes from the other chapter. So do we like 2.86? For our pH? Any questions on this one? And so the last one, so what was this one? Do you remember the definition? So we have the pH at 1/2 the equivalence point. Do you remember from the notes what this was? Yeah, the pKa. So this is just our definition. So going back, right, our half neutralization, so our pH equals our pKa there. So pH equals pKa. All right, that's probably how much time we have. But we'll pick up on Thursday, so we'll probably look at your homework problems and we can kind of keep practicing that. So that's kind of what we'll keep working on, right? Calculating our pH at these different points, kind of looking at our titration curve, and then lab will really emphasize that.